Hello. So what we've been doing so far is look at examples of sets in Euclidean spaces that may and may not look similar to the familiar manifolds. In particular, we saw examples of counter sets, self-similar or otherwise, and we also looked at the precise study of self-similar sets, how they are defined, and how to look at their Hausdorff dimensions. We talked about Hutchinson's theory giving explicit formulas for the Hausdorff dimension of such sets. So what was the conclusion and what was the goal in doing so? We wanted just to have a collection of sets so that we can motivate the theory of geometric measure theory of sets excuse me, that follows. For example, by looking at the four-corner counter set, which was featured in at least two of the videos, and we looked at it in two different ways, using constructions as in one and also constructions as in two. What is true about this set is that its Hausdorff dimension, I'm going to call this C, is equal to 1, and its Hausdorff measure is finite and positive. So from the point of view of just Hausdorff dimension and measure, it shares properties of, say, a C1 curve. That is, these properties are shared by more familiar one-dimensional objects. Namely, if you have a C1 curve, then this also has Hausdorff measure 1, let me call this E, that is finite and positive. But then, if there's just this, we shouldn't regard these two sets really similar. E is very different from C in every aspect that we can imagine. So how does geometric measure theory distinguish between these two sets? And in fact, that is one of the goals, the main objectives of geometric measure theory. So indeed, geometric measure theory was started by, so keep those pictures in mind, by Besikovich, who, as Mattila says, to an impressive degree, studied sets in the plane with finite Hausdorff measure. So we can call them of finite length. So the question, the very fundamental question was, what does a set with finite and probably also positive Hausdorff measure really look like in the plane? To what degree can it deviate from looking like a C1 curve? And to what degree is it similar to that? And really what followed was first generalizing his ideas to arbitrary dimensions, and of course then many, many deeper results followed. And I'm going to give a brief summary of some ideas with plan to follow up on more details in future videos. Okay. So we saw two very different types of one-dimensional sets in the picture that I just showed you. The four-corner counter set versus a genuine C1 curve. The type of curves, sets with finite H1 that exhibit behavior similar to the curves will be called rectifiable. So a rectifiable set, so it's just a set in R2, you can keep thinking, is a set that, so this of course very imprecise, that looks like a C1 curve, an honest curve, from measure theoretical aspects. So because there is some measure theory involved, you can, for example, always adjust the set by adding or deleting a set of measure 0, and you should be able to ignore them. So up to measure 0 sets, for example, they look like C1 curves. So, but what does that imply for the set? What is special about being C1 curves? Okay, such sets share three main features of C1 curves. So in what ways do they resemble smooth curves? Number one, let me maybe keep some room for later. They admit an approximate tangent, whatever it is, at almost every point of them. So a C1 curve has a tangent line at every point. So of course that has to be relaxed to almost every. That means those points where it does not admit will have measure 0. And also the notion of tangent in the classical sense is too strong to expect from measurable sets, so that is also relaxed to approximate tangent. Of course, these all need precise definitions for them to really make mathematical sense, but for now, that's as much as we want. So number one, so that's the number one property they share and makes them similar to C1 curves. The next one is that projections onto lines. So again, we're thinking dimension m equal 1 in Rn, where m is less than n and both are integers. So projection of this set onto, again, we have to sacrifice something, almost every line has positive H1 measure. So let's look at the example of the curve again. So curves definitely have that property. So if you choose some direction and you project your set onto it, maybe that wasn't the right color, so you orthogonally project it onto that line, and you will see this green part, which has positive measure. And this is true for almost every line. Notice that even if you have, you only deal with smooth curves, this almost everywhere is necessary because, for example, in my other picture, if your set happens to be, say, vertical, then projection onto x-axis actually becomes only 1 point. So that is not really coming from a rectifiable sets. It's true even for smooth sets. We saw this before. Actually, we gave a proof that for the four-corner counter set, projection onto almost every line has 0 H1 measure. In fact, there, the set of lines where the projection was significant had measured 0. In fact, maybe 1 or 2 lines. We had only 1 or 2 lines where you project this four-corner counter set onto, and you see some positive measure, and otherwise you would see only a set of measure 0. So the exceptional line was y equal 1/2 x. If you project onto this, the blue part, you will see some set of positive measure. This will have positive measure, but if you change the angle in any way, then the projections are not of positive measure. So we're looking at a one-dimensional set whose projections, whose shadows are not one-dimensional. And so the shadows really do not capture the set, which is weird. And that's just natural because the four-corner counter set is not rectifiable, and it's one of those weird sets. And property 3 that rectifiable sets share with C1 curves is that of density. Again, we will talk about the definitions later, but roughly speaking, it says that at almost every x from your set, the measure of the ball of radius r in your set, so because E is sitting in R2, you can think of this as the genuine ball in R2, but of course you're only interested in the set E, so you intersect with that, and E is receiving the induced metric from R2, so you can regard the E as a metric space on its own. So you can also say this is the ball in the intrinsic metric of E. But anyway, however you look at it, this is the same set, and now the claim is that if you are like a C1 curve, then let's say for very small r, that means as r goes to 0, if you zoom in around the point, the measure of this is getting very close to what you would see in the real line. So the one-dimensional, let me first draw the picture. So if you are in R1, which is the most typical one-dimensional object in the universe, and if you look at a point x, and you look at the radius r, the ball of radius r, which is not really a ball, but technically from the definition, mathematical definition, it is r. So you get r on this side and r on this side. So its measure, its h1 measure is 2r. If you look at a one-dimensional curve in R2, which is C1, and then, and if you take a point x, and then you take the ball of radius r, so the part of the set that lies inside the part of the ball that lies inside your set will be this. Okay, and the ball has radius r. As you can see, it's not really expected that the length here will be exactly 2r, but also at the same time, it's not difficult to believe that as you let the radius go to 0, then pretty much it is equal to 2r. And being a C1 manifold means that if you zoom infinitely strongly for a C1 curve, you will not be able actually to tell it from a C1 curve. So it will be very, very, very close to being just a segment. So when you zoom out, it will be like exactly like what is in R1. So this is for subsets of R1 and C1 curves in R2 or in Rn in general. What this property 3 says is that for rectifiable sets, that behavior will persist. You will keep having the fact that the measure of ball of radius r is what you expect from a line segment in the Euclidean R1. And that is no longer true for sets that are not rectifiable. Again, that property 3 fails for the four-corner Cantor set. And the failing, at least we can make precise. Okay, so one way to make this star precise is to just form this H1 measure of ball of radius x and r, and then divide by 2r, and then ask about the limit as r goes to 0. But we're never sure if the limit even exists, and that's why mathematicians have invented the amazing notion of lim_sup, which always exists, and lim_inf, which always exists. Okay. So we say density exists at x if and only if these two guys are equal. So we call this the upper density, and we call this the lower density at point x of the set E. At point x of the set E. And also because we're looking at H1 measure, so this will be density 1. Okay, so that is what densities will be. We'll define them for arbitrary dimensions and not just one. So the property that rectifiable sets, here we're talking about the one rectifiable sets, have in common with C1 curves is that this density, at almost every point, these densities both exist and coincide with the number 1. At almost every x, these will converge to 1. And with the four-Cantor set, it will be the case that this will be strictly less than that on a set of positive measure, probably actually at every x because of self-similarity. Okay, how am I so certain about this fact, this claim about four-corner Cantor set, even though I have not really computed that density? The reason being is that, and the more deeper actually theorems, the more surprising facts about rectifiable sets is that each and every one of these conditions, 1, 2, and 3, have a converse. So we said that if you start with a rectifiable set, they have the properties 1, 2, and 3. But then, if you start with an arbitrary set, almost arbitrary, and then you show that 1 is true, from that, you deduce that it is in fact rectifiable. Which means then that the other properties 2 and 3 also hold. So even if you don't know at this point, I didn't give you the very definition of rectifiability, you can rephrase it in the following way and still see how surprising it is. So what we're saying is that if for a set, property 1 holds, then property 2 and 3 also hold. And for example, this probably is, it's safe to say that this was, well, for dimension 1 in R2, it was proven by Besikovich, and the generalization for this one probably, it's safe to say, was due to Federer. Number 2, that if projections behave the right way, then your set is rectifiable, is, again, in dimension 1, it was Besikovich, and then for arbitrary dimensions, Federer. Property, converse to 3, the fact that if the density exists almost everywhere, then your set is rectifiable, is very, very deep theorem of Price. Here also I must mention that we can define for S arbitrary these densities, and then there is the theorem of Marstrand, again one of the deep theorems of geometric measure theory, that if, say, S density exists, then S is an integer. That's again quite surprising, because look at the definition of density. So all you will do is put S here and then replace this by power S and the right constant used in the definition of Hausdorff measures. So just because these upper and lower limits, lim sup and lim inf, exist almost everywhere, HS almost everywhere, is not clear at all that will force S to be an integer. So why can't you have that equality in non-integer dimensions? Okay, so this is also probably fits into the third condition. So there is this, but once you know that S is integer and the density exists almost everywhere, then the Price has proven that your set must be rectifiable. Okay. The other extreme are what we call purely unrectifiable sets. So the purely unrectifiable sets, so you may think, okay, we have some one-dimensional sets that really look like curves. They have all these properties 1, 2, and 3. And then there is the four-corner counter set, which failed the density, failed the projections, and failed this, we didn't talk about this, but it also fails the approximate tangent property. And then you can imagine, and then there are sets in between. But fortunately, and very fortunately, that does not happen. So it's kind of nice that either you are rectifiable and you have all these beautiful properties, or you're purely unrectifiable, which means you are complete opposite of these. You have none of these. So kind of there is no in between. And then by exhaustion argument, very generic exhaustion arguments as a measure theory, you can show that every set is union of a rectifiable piece and a purely unrectifiable and this is unique basically up to measure 0. So if you're talking about H1 rectifiability, you're talking about one-dimensional sets. Of course, you can toss in 5 points here and there. You can either drop them or add new 5 points. And from the point of view of H1, nothing has happened. So that's why this up to measure 0 subsets is necessary. You can also just pick some points from the rectifiable part and toss them into the purely unrectifiable part. So a very stupid example here would be that you have your 4-corner Cantor set, and then that's purely unrectifiable, and then you can union it with a C1 curve. So for this set, the purely unrectifiable part will be everything that belongs to the 4-corner Cantor set, and the rectifiable part will belong to that. So the amazing thing is that every set can be decomposed this way, and then we know exactly how the rectifiable part and the non-rectifiable part behave, and that the set you start with is union of the two pieces. Okay, the issue of rectifiability. So there is an important thing about rectifiability that I was discussing. It was that it's meaningful and it concerns only integer dimensions. This is because definition of rectifiability is motivated by comparing sets to subsets of the Euclidean space of that right dimension. So if you're looking at 2 rectifiable sets in R3, you're comparing them to pieces of R2. And with the examples above, I was looking at 1 rectifiable set, so I was comparing them to subsets of R1. Well, curves are comparable to subsets of R1, and 1 rectifiable curves sets are also. So rectifiability by its very definition concerns the integer dimensions. But how about non-integer dimensions? So if S not an integer, what can we say about these 3 properties? So tangents, can we talk about them? Can we talk about projections? Of course, we can talk about projection, but can we say anything about the dimension of a projection? What will a generic projection produce? How will the dimension drop? And then densities, which can be defined, as I just mentioned, for all dimensions. So this one is out, but we will see that there are general theorems about this one and also about densities. And this will be my the subject of my next few videos, where I will go into more details about densities and in arbitrary dimensions. Now I want to introduce you to a very, very beautiful resource on YouTube. So Azzam has made some beautiful videos on geometric measure theory, which emphasizes, so the topic and the main focus of those lecture notes, those lecture videos, about 50 of them, is on rectifiable sets. They are beautifully made and without proofs and lots of examples, but he occasionally does give proofs and gives a general broad idea of the concepts involved. I will put a link in the description to the channel and also to specific videos. For example, the ones that discuss density or the Price's theorem or Marstrand's theorem. So I have been aware of these videos for a long time, and I've watched many of them myself. So my goal here will be to avoid too much overlap with his. So if he's done and covered something really nicely, then I wouldn't dare to redo them, and there's no need for such a thing. So instead I will focus on maybe things that he hasn't really emphasized on, and also occasionally I will give proofs of kind of nice things that I think will be worthwhile to see. Some proofs are just illuminating, like other proofs that are just technical. So there's some merit in seeing proofs as well. So in particular, I will focus more on non-integer cases, dimensions. We will just give more examples wherever possible to illustrate the theory more, and some proofs also will be presented for some of these facts. Okay, so the main resource we've been using, as you all are aware of, is the book by Mattila. So chapters 6 to 14 are for all dimensions, integer and none, and then chapters 15 to the end of the book cover rectifiability, basically. So it's limited to integer case. So that is the structure of the book by Mattila. Geometry of sets and measures. So here I must also mention the book by Falconer, whose exact title, unfortunately, I don't want to make a statement about. So this book deals with integer and non-integer in separate, clearly identified chapters. So they deal with some, for example, for the range s between 1 and 0, and then they talk about s equal 1, and then s equal to integer arbitrary, and then s non-integer and bigger than 1, things like that. So that book also has a clear breakdown of the range of dimensions. Okay, so that's kind of a crash course, or let's say a review or summary of what geometric measure theory of sets deals with. Really, it comes to three properties of projections, tangents, and densities. And this looks only deceivingly simple. As I said, that each of these characterizes rectifiability in integer dimensions. Each one is a deep theorem of geometric measure theory. For example, Price's theorem itself can be regarded as a small, I don't know, a small book can be written on that proof. Okay, so next few videos, as I said, will be about this density, how it's defined, why is it defined even, what was the motivation behind it, and from there we will keep going. So thank you for following this video so far, and if you have, that means you have actually liked it, in which case you should consider if you have subscribed to the channel or not. And with that, I say goodbye and have a nice day.